Hi, so today we'll practice big O notation and complexity analysis, which is a crucial concept for any programmer. So the expected outcome for the course is that you should be able to look at some simple functions and be able to analyze and determine its big O complexity. In our case, it will be the worst case complexity. So for Comp 1010 students, we expect you to be able to demonstrate your analysis and calculate the time complexity in the final exam. Big O notation helps us describe the efficiency of an algorithm and in terms of the time it takes relative to the size of the input. Hopefully you should know that by now. It's a way for us to express the worst case scenario for how long an algorithm will take to run. So today we'll take a look at some examples of some different complexities. And for each following example, please pause the video for a couple minutes to read the code snippets and try to analyze it yourself. And then write down your answer. After a few seconds, I will explain the solution. So please remember to pause the video for each example and attempt to come up with a solution yourself before moving on. Okay, so let's start with example one. Example one, you should be able to guess the complexity of this function quite quickly now. Please pause the video if you have not been able to identify what time complexity this has. So I'll wait for a couple seconds and then I'll explain the solutions. Okay, so our first example is a simple function that sums up the elements in the array. It runs through each element once. So as you can see in this for loop for element in our array. So that means it goes through each element once. So, and inside that loop, for each element, it just adds it to the total. Adding is a constant time operation, which means it's O1, so we don't have to worry about that. This loop is complexity of ON, where it's talking about n being the size of the input array. This means that the time it takes to run is directly proportional to the size of the input array. Here, the number of operations is equals to the number of elements in the array, so hence a linear relationship with the input size. Okay, so let's move on to example 2. Here, example 2, what do you think is the complexity for this function? I'll pause for a couple seconds. Please take some time for you to figure this out yourself. Please pause the video if you need to, and I'll continue with the solution in a bit. Okay, so we have a function to find the maximum element in an array. Similar to the summing function, it checks each element once. So you can see that it's 4 element in array. It checks if element is more than the maximum. This comparison is a constant time operation. Assignment is a constant time operation. So this basically just depends on the for loop, which is proportional to the linear time of the size of the array, which is O of n. The function iterates through the array once, and the number of comparisons it makes is also linear with the size of the array. So we utilize the knowledge that fundamental operations like comparisons and assignments are constant time to do our final analysis. Okay, let's move on to the next example. This one is a bit more complicated. Please pause the video now and do your own analysis. Okay, so this one is a bit more complicated, but it's not a hard one. Even if you recognize this function, please take some time to do your own analysis from the ground up to find the complexity. This algorithm here, you can see that it uses 2 nested loops. Okay, so this is where it gets interesting. So this uses 2 nested loops. You can see that the range is different for each. The first loop is range to n, second loop is range from 0 to n minus I minus 1. So this is where the problem might begins. But you can see that the outer loops runs n times. and the inner loop runs n minus I minus 1 times per iteration of the outer loop. So in the worst case, the total number comparisons is the sum of n minus 1 integers, right? So it's basically the sum of n minus 1 integers, which is n minus 1 times n over 2. So I'll write this out. So it should be n minus 1 times n over 2. So this equals to O of n squared. Hopefully you can see why it's O n squared, because if we expand this out, it's n squared minus n over 2. And we reduce this to O of n squared. So the time complexity is O of n squared for this case. Please, if you are not familiar with what just happened, please revise the lecture notes and then come back and reattempt this example again. Okay, so moving on to the next example. Please pause for a few minutes. Okay, so this one should be a little bit easier than the first one. You can see that there are two for loops here again, nested for loops, and the range is the same. So it's all range on n, the length of the input array. So this is quite easy. You can see that for this inner loop runs n times for each iteration of the outer loop, which means it's n times n, which is O of n squared. So this is O of n squared. Let's move on to the next example. This one should look a little bit familiar to you, but please take some time to think of to try to analyze each step and figure out what the complexity is. Okay, so hopefully you should have found that this is O of log base 2 of n. And why is that? That is because after each iteration of while, the while loop, you can see that left, the condition is left smaller or equals to, less than or equals to right, right? And left is from 0, right is from the length of array minus 1, so basically the two ends of the array. And how does this condition differ after each iteration? It is when you change either left or right. Left or right can be mid plus 1 or mid minus 1. And mid is basically the middle point of left and right, left plus right. So you can see that after each iteration, the array is down to half of the previous size. So it keeps halving, and if you write down the equation, you will be able to come up with that the number of times it halves is log base 2 of n. So this is complexity is O of log n. We don't really care about the base in big O complexity, so you just need to write O log n, and that's enough. Okay, for the next example is example 6. Please pause for a bit. Okay, so for example 6, here this is might not be quite familiar to you. So in this case, where you have a magical coin that doubles in number each day, right? This function calculates how many days it will take for the number of coins to reach or exceed a limit starting from a certain amount. Hopefully you can see that this is the reverse of what we did for example 5. So in example 5, we halves every day, every iteration, but in example 6, we're doubling every iteration. So this is also logarithmic because the number of coins double each day, so the time it takes to reach the limit grows logarithmically with the size of the limit. So example 7, This is a recursive function. Hopefully you will be able to figure this out. Okay, so example 7. The function makes two recursive calls for each non-base case call. So this is a base case, and the non-base case, which is the recursive case, it calls the function itself 2 times. 1 for n minus 1 or 1 for n minus 2. If you draw this out into a tree, you will be able to see that the number of calls grows exponentially with n, and it forms a binary tree with height of n. So the number of calls is 2 to the power of n, which is the worst case, and the time complexity of this function is 2 to the power of n. As this one is quite hard, so please draw out the function call in a tree and you'll be able to identify the pattern from there. Let's move on to the last example. This one is quite tricky, so please take some time to figure it out. Okay, so the number of subsets with n element is 2 to the power of n. So because each element can be either in a subset or not, right? So imagine if you have a room of 10 people and each people can be present or absent. The number of possible configurations of that room is 2 to the power of n, because each person can be either absent or present. And the recursive process generates all of these subsets. So you know that at most it can be, in the worst case, it has to account for 2 to the power of n cases, because it generates 2 to the power of n elements. So the time complexity here is 2 to the power of n. Okay, so this is a very brief video. Please reach out to me if any of these cases confuses you. I try to keep this video short so that you guys don't get bored throughout the duration for those who already understand this. But if you need clearer explanation for each of the cases, please reach out to me and then I'll get back to you with the more detailed explanation. So in conclusion, through this study session, we have explored various examples that illustrate different time complexities. Understand these complexities critical for you to assess the efficiency of an algorithm, which is an essential skill required for your exam. Remember that big O notation primarily focuses on worst case scenarios, but in practice, the average case often holds more relevance. But this is just for the theoretical analysis, so we care more about the worst case. So please keep practicing these examples until you are finally able to get it right. And yeah, good luck with your exam.